Today I'd like to talk about least squares regression, so open up your study guides to the least squares regression section. Now in algebra, we typically refer to the variables in a linear regression equation as the independent variable x and the dependent variable y. However, in a least squares regression setting, we have specific names for these variables. We let x be the explanatory variable, and the variable y is called the response variable. We use the explanatory variable x to predict the response variable y. So in a regression setting, it's a little bit different than what we've typically known our variables x and y to be in algebra. Once again, our independent and dependent variables in a regression setting are called the explanatory variable and the response variable. And once again, we use the explanatory variable to help us predict responses. Now we refer to the least squares regression line as the LSRL. From this point forward, in our use of statistical terminology, we can just abbreviate LSRL, and we know that we're referring to the least squares regression line. Now here's the equation for the least squares regression line. Y hat equals A plus B times x. It's a very simple linear equation. A represents the y-intercept of the LSRL. It's basically the height of the line when x equals 0. And in context of the problem, the y-intercept sometimes has meaning and other times it does not. It all depends upon the problem situation. Now B represents the slope of the least squares regression line. It is the amount by which y increases when x increases by 1 unit. The sign of the slope will determine the direction of the least squares regression line and will determine whether the correlation coefficient is positive or negative. So although it's a very simple equation, it's just a linear equation, the y-intercept and the slope have important meanings in our study of statistics. And once again, the sign of the slope is going to determine the direction of the least squares regression line, and it will determine whether the correlation coefficient is going to be positive or negative. The definitions of both the y-intercept and the slope are going to become very important when we talk about actual problems involving least squares regression lines. The LSRL is the line that gives the best fit to our bivariate data. Once again, the least squares regression line is denoted by y hat equals a plus bx. Don't forget to put the hat on top of the y. The hat on top of the y is going to tell us that we're having predicted values based on a model. This statistical notation is used to let us know that this is a predicted value based on our least squares regression line or the line of best fit. By definition, the least squares regression line, the LSRL, is the line that minimizes the sum of the squares of the deviations from the line. So mathematically, the least squares regression line is built in such a way that the sum of the square deviations are a minimum, and this gives us what we call the line of best fit. Now let's take a look at an example here. We've got 3 points, 2, 0, 5, 8, and 10, 5. Now let's consider the following line. Y hat equals 3 plus 0.4x. This is a line that's going to be used to predict values based on these data points, and it certainly seems like this line fits the data very well. But is it the line of best fit? Let's calculate the deviations. Now based on this predicting line, we would have the following 3 points. The points on the line represent the predicted y hat values based on the model to the right. To get the deviations or residuals, we take the actual y value and subtract the predicted y hat value, that is y minus y hat. So our first residual value is going to be equal to 0 minus 3.8 or negative 3.8.